The most remarkable thing about direct-to-device is not the satellite, it is the phone in your pocket, the one nobody redesigned. For decades, satellite communication meant a bulky terminal with a directional antenna and dedicated hardware. D2D broke that assumption by redesigning the other end of the link instead. That is the inversion worth understanding. Historically, when engineers needed more link performance, they made the user terminal bigger, more powerful, and more expensive. Direct-to-device does the opposite. It deliberately shifts complexity of the handset and into the space segment. Huge phased arrays, advanced beamforming, very sensitive receivers, heavy onboard processing. Every engineering decision in this course served one goal: keep the smartphone as ordinary as possible. So do you need a special satellite phone? For first-generation D2D systems, usually not. A modern handset already carries a wideband RF front end, a sophisticated digital baseband, multiple antennas, and a highly integrated modem, supporting many cellular standards. Those parts were built for terrestrial LTE and 5G, but a good number of them already operate inside the frequency ranges allocated to satellite services. The hardware foundation is already sitting in millions of phones. What actually changes then? Almost nothing physical. Antennas, power amplifiers, low noise amplifiers, RF transceivers, and baseband processors stay essentially as they are on supported devices. The changes live in firmware, which enables additional operating modes for non-terrestrial networks, extended timing, advanced calculations for much longer delays, satellite ephemeris processing to predict where the spacecraft will be, Doppler compensation for high relative velocity, modified HARQ timers, and extra synchronization procedures tuned for a fast-moving satellite. That distinction has a real consequence. None of those functions needs new silicon. So many phones already in service can become satellite capable through a modem software update, which means commercial availability depends far less on handset electronics than on four other things: firmware availability, operator certification, regulatory approval, and service activation. Synchronizing is the hardest part of the modem's job. A tower stays put. A LEO satellite moves at 7.5 kilometers per second, changing both its position and its relative velocity continuously. So the modem combines several sources at once: ephemeris, data, to predict where the satellite will be, timing advance, to absorb the longer propagation delay, and Doppler compensation to keep adjusting transmit frequency. All of it runs continuously, and all of it is invisible to the user. Now the transition between terrestrial and satellite coverage. From the user's point of view, it should simply not be noticeable. And notably, the phone does not decide. The network continuously evaluates radio conditions and picks the access technology, exactly as it does between LTE and 5G, or when roaming. When terrestrial quality drops below threshold and satellite service is available, the network initiates a handover toward a satellite cell. There is one extra wrinkle: satellite cells move, so the handover message must also carry the satellite's predicted position, its timing parameters, and its synchronization requirements. Once synchronized, the device simply carries on with familiar LTE or 5G procedures, and these handovers are network-controlled rather than device-initiated, which lets operators reserve scarce orbital capacity for the users who genuinely need it. Where does that leave the market? Many recent flagship devices, built on current Qualcomm Snapdragon and MediaTek modem platforms, already carry most of the hardware needed for NTN operation. Early deployments have concentrated on narrowband emergency messaging. Later generations are expected to extend toward voice, Internet of Things, and eventually broadband. Through all of it, the handset is expected to change relatively little. The advances keep happening in space. To close, D2D inverts the traditional model. The satellite gets more capable, so the phone can stay ordinary. Most of the hardware is already there. The barrier is software, certification, and spectrum. Synchronizing with a moving satellite is a firmware problem. Handovers reuse 3GPP mobility and stay under network control. And the greatest achievement is that the user never notices any of it.